Hello everyone, welcome to our presentation. My name is Nicholas Johnson and I am here today with Jamil Balas, Zad Anwar, Harpal Deol, and Saurav Singh. Today we'll be discussing current protection schemes against overhead line faults causing wildfires in California, as well as a new design that may help us pinpoint the location of a fault in a distribution system more accurately and faster than what current technology has to offer.
For many years, California has been in a drought, which has led to conditions favorable for wildfires with all the excess of dried out vegetation. This, along with the changing weather conditions we are currently experiencing, such as high winds, is contributing to challenging conditions for our overhead power delivery infrastructure. In the past year, one of the biggest public utilities, PG&E, had to file for bankruptcy following fires which were caused because of equipment that had failed and caught on fire. This in turn led to thousands of acres burning up and taking out a whole town, with many lives lost. In 2020 alone, fires have consumed over 4 million acres in California. Thus, in the modern age, we need to try to be as proactive as possible to reduce the risk of injury and even death by such conditions. By being able to detect faults in power lines, we can reduce the number of lives lost.
A little over a year ago, this project was started by another group of CSUS seniors with the same intent to detect and prevent massive wildfires. This project is a continuation of theirs. We are designing and testing the effects of an ultrasonic signal transducer that is mechanically tied to a distribution line that transmits an ultrasound wave. Some of our research included finding the best transducer to start our testing, but after some discussion with the last group, they handed theirs over to us. The transducer passed down to us is made by Yay CCC, a company that specializes in designing both high and low powered voltage transformers and other industrial electronic machines. A transducer is very useful to us because it allows for a signal that is not electronic, like a sound signal, to be converted to something that is useful to us, like a voltage signal. An ultrasonic wave will be transmitted to a distribution line via transducer and returned back. If a line is operating as it's intended, the ultrasound signal will return to the transducer with very little distortion. However, if the line is faulted, for example a single line-to-ground fault or a line-to-line fault from a closed tree branch, the transducer will not receive the same signal, but rather one or more very distorted signals. This short clip explains a little more in detail of how the signal will be sent on the line and received by the transducer.
With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse.
This second image is illustrating the stages of the ultrasonic signal and what the transducer is doing. First, we begin with the transducer transmitting the ultrasound wave on the line, which gets recorded as a voltage. The wave then travels along and returns back to the transducer to get read and then finally converted back again to voltage. We will be able to use the information to search for fault locations on the line using wave reflection and comparing the ultrasound signals on both sides. This will give us exact locations of faults. This system will be able to provide live feedback of what is occurring on the distribution lines, so we are able to detect, repair, and potentially fly out to a fire site as soon as it is ignited.
There are several practical ways that ultrasonic technology is being used today. For example, medical imaging, autonomous driving, monitoring fluid levels in large tanks, as well as several other applications. Our project takes advantage of the fact that it can be used to detect impurities in metals. Ultrasonic waves can be sent along metal pipes to detect debris and corrosion. However, our project is a bit more complex. A majority of modern distribution lines are made of all aluminum or aluminum conductors with a steel core. Although we know the typical speed of sound in these materials, we do not know how the ultrasonic waves will respond to the braided conductor. There has been no research or testing on this subject, so we will be doing physical experiments on our distribution line model. Our goal is to understand the characteristics of this ultrasonic wave in an all-aluminum conductor distribution line. This information will help us develop an algorithm to determine abnormal behavior and distorted return signals indicating a fault or damage to the line. The California Public Utility Commission estimates that about 10% of wildfires are caused by power lines. In most cases, the power line fault is caused by a nearby tree or branch coming into contact with the line. According to a 2017 study, the majority of tree conductor contacts result in high impedance faults of low current, meaning that modern overcurrent relays may not detect a lot of these faults. According to the study, there are 4 species of trees that pose a high risk of faulting. Of those 4, the paper birch trees are very common in eastern California, and the ponderosa pine is found in the Coast Range, Cascades, and throughout the Sierra Nevada all the way down to San Diego. The distribution lines in these areas pose a huge fire risk. The most effective solution would be to bury the power lines in high-risk areas. However, doing so can cost up to $5 million per mile and can take several years. Ultrasonic fault detection is a great alternative for adding an extra layer of protection against tree faults in high-risk areas. According to Eaton Cooper Power, a large manufacturer of power equipment, a majority of faults are temporary. These temporary faults are easily cleared through the use of a recloser. After a fault is detected, a recloser opens and closes multiple times. If the fault is not cleared by the final attempt, the recloser locks out until it is manually reset once the fault is located and cleared. The blackout from the recloser can last several hours, and by the time the fault is located, it may be too late to prevent large fires or damage to equipment. With the existing infrastructure of reclosers, an ultrasonic sensor can be added to the control module. The ultrasonic sensor will send a signal every time the recloser opens in order to accurately locate the fault on the de-energized line.
This new age fault detection scheme can add an extra layer of protection to what we already have in place. Current protection schemes are designed to stop a fault from happening after it has already happened. With this, we are being proactive and setting up a system to detect a fault while it's happening. This method of protection will also work whether the distribution line is energized or not, because the ultrasound wave is added to the line externally from generation. Additionally, it is operating at a much higher frequency than what our electricity runs at, so reading something like 60 Hz on our meter will not be something to alarm us. With ultrasonic technology on the line, it will be obvious to us when there is any break in the line and where it is, regardless of how much current is on it. PG&E has already conducted a case study in various regions of California that demonstrate the use of traveling wave theory to find fault locations. These plots here show an example of a traveling wave that was sent on the line to find where it is faulted.
To ensure that we achieve the goals of our project, we have laid out a rough schedule. From August through October, we conducted research on the project and made sure that our team was aware of every aspect of how the project will be executed. After that, we figured out which components we need for this project and developed a plan for testing. From December through January, we are figuring out the connections between the devices used in the project, and hopefully we'll be able to get access to a lab this month to run the first simulations. After that, we'll be working on the signal detection software, and we'll ask for help from the professor and his team if available. From March until the end of the spring semester, we'll be working on a lot of simulations that use the device and the software to make sure that errors are reduced to the minimum. In order to avoid time waste and to have a clear view of what is the next step and what's the time range for it, performance reporting is mandatory. We have different methods that will help us stay on track and give us enough time to maintain high quality work. First, we are using weekly individual and group journals. Second, we are asking for guidance and discussing progress made through the weekly meetings with the professor. Finally, we are measuring the progress made against the plan by multiple weekly meetings and COVID-safe in-person get-togethers.
As stated previously by our group members, we are further developing and implementing on a previous project. Thus, we have used the previous group's information as a starting point, and we will be making the necessary changes required to further develop this new technology. The changes that occur when our project is in motion will be scrutinized to make sure our end goal is not jeopardized. These could be new ideas or certain situations, such as if one group member gets sick. We would then divert that group member's work evenly to other members. Our ultimate objective is to keep our workflow towards our project in motion while also being open to the changing situations at hand. This is especially important with the current COVID pandemic storming through our world.
We know that high voltage systems are a safety risk. However, our new age design will be created with a low voltage source to use in line with current high voltage distribution lines for fault detection. We proactively created cushions within our schedule to allow for delays, mainly around the transducer to learn its operations. We have also done our part outside of the lab to examine the parts and data sheets to have the most time for in-lab experiments. An additional risk we faced was getting sick to COVID-19. We have taken the necessary precautions to avoid personal contact with each other as much as possible. However, meeting in person to improve our productivity was sometimes necessary. We were and still are doing our best to comply with university and state regulations to make sure everyone stays healthy. To keep our system at an optimal level, we are making sure to use an ideal transducer to give the best outcome as far as reliability, working under the expected conditions, and being cost-effective to repair and replace all at the same time. Also, we plan to keep testing at a low voltage until we know the system functions as needed, then using it near high voltage systems. Low voltage testing also helps prevent damage to our equipment, as it is hard to reorder materials and we are not always able to work together to resolve issues. We are also continuing from the previous group's data and materials to keep all findings similar and from the same system. Lastly, we hold group meetings where we discuss ideas, findings, and solutions prior to making them permanent in our project. Thank you all for tuning into our presentation. We hope it was very insightful and educational. Here on the last slide, we have our sources and contact information.